I'm going to assume that you have watched the previous lecture already, and you know this problem involving assembling trains. And we were looking for a pattern in the answers that we came up with there, and came up with, in fact, a formula that captured a certain pattern. So let me remind you a little bit about this. The problem was about putting together trains out of two kinds of cars, locomotives and coal tenders. And there were certain rules that we had to follow in putting together trains. I then asked, well, suppose I tell you the number of cars you're allowed to use. Let's call that n. Then how many trains can I build? Well, if we call that number t sub n, then looking at certain cases where there's just a few specified cars, we observed a very interesting pattern, very simple, expressed by the formula that's given here, which says Tn equals Tn minus 2 plus Tn minus 1. That is to say, you can calculate the number of possible trains having n cars if you already know the number of possible trains having n minus 2 cars and n minus 1 cars. It simply says add those two known values and you will get the value that you want. This partly came from filling out a table like this, but actually most of this table comes from using that observed pattern, assuming that it continues, and therefore calculating the values at the bottom. So let me perhaps say a little bit more about that. So I asked you to think about the number of two-car trains, and there's only one of those, and the number of three-car trains, again, there's only one. And there were two four-car trains. We also observed that there were three five-car trains and five six-car trains. You could also think, maybe you didn't think about this, but you could also think, well, what about one-car trains? Well, there can't be any of those. There is zero. It's impossible to have a train satisfying the conditions. So all this evidence, when looked at, suggests this pattern that we observed. And remember, it went like this. If you take any two numbers in this column, for example, the successive ones, and add them, you get the next one, which is 2. If you add 1 and 2, you get 3. If you add 2 and 3, you get 5. Now, all of that is captured by that formula, Tn equals Tn minus 2 plus Tn minus 1. Of course, we only observed it for a few values of n. We observed it for n equal to 3. Oops. Let me come back to this. For n equals 3, we saw that it was correct. For n equals 4, for n equals 5, for n equals 6. And then we made a wild guess, wild in the sense that it's just a huge guess, that these numbers would continue to follow that same formula, that is to say, that same pattern forever. If that's true, then you get to infer that the number of 7-car trains is 8, and the number of 8-car trains is 13, the number of 9-car trains is 21, and so on. So if you make this assumption, which is indeed a huge assumption, you get a lot out of it. You get, in fact, this whole sequence of numbers, as we're going to call it. Now, the thing I want to say is it's so beautiful that you're tempted to believe, well, this must be correct, right? That's very often true in mathematics. You see something so simple and elegant that you say, that must be the pattern. But you see, we haven't really proved that it's correct. We just know that it's correct in the cases that we have already mentioned, namely n equals 3, 4, 5, and 6. We do not know that the formula is true for this range of values of n. What I'd like to do in the remainder of this lecture is to show why the formula is true. Now, how could you check whether you're getting correct values? You could see whether they actually fit the actual count of number of trains. For example, if you go back to this table, it's making a certain prediction. Even though you haven't worked them all out, it's predicting that the number of 8-car trains is 13. There are 13 legal 8-car trains, according to this table. Is it really true? Well, one way to check it would be to actually build all these trains. But even if you did, that would just be checking one case. You'd still be left with other predictions. So what about the claim that T13 is 144. In other words, there are 144 trains with 13 cars. It certainly would take a lot of work to check such a prediction, and probably you'd get tired and make a mistake along the way anyway. So you should feel that this is sort of unsatisfactory. You can check as many individual cases as you want, but in mathematics, what we really want, what we really need, is an airtight logical argument explaining the observed pattern. That is to say, we need a proof. Well, why is the formula true? I'm going to explain it. First of all, let's do a warm-up example. Let's suppose that we already know all the 6-car trains and all the 5-car trains. And let's try to build 7-car trains. Now, when you begin to think about it that way, you'll realize that there's sort of a systematic way to do that. What you can do is you can start with a 6-car train and then put an extra car at the end. I'm showing you this as an example. If you have LCC, LCC, you can throw another C on the end, right? And that's a legal train, since all we've done is to stick this C on the end, and we're always allowed to do that. So anytime you have a 6-car train, you can make a 7-car train out of it just by sticking on this extra coal tender. However, this does not give all possible 7-car trains. There's a second method. Here's what I'll call method B. The previous one was method A. This one is method B. Now start with a 5-car train. Well, you've got to put 2 extra cars on, but this time you can put an L and then a C. So method A was to start with a 6-car train, put C at the end. Method B was to start with a 5-car train and to put LC at the end. Now, these are summarized now in this side-by-side analysis. Method A was start with a 6-car train, put C at the end, and I claim that gives you all the 7-car trains which end in CC. Well, how do you know that? If you have a 7-car train ending in CC, then you can take the C off the end and you're back to the 6-car train that it came from. On the other hand, if you use method B and you start with a 5-car train, well, you're putting on 2 letters at the end and they are LC. That's going to, of course, give you trains that end in LC. And anytime you have a 7-car train ending in LC, you can see what it came from by taking the LC off, okay? So method A gives you as many trains as you already know there are for 6-car trains, and method B gives you T5, right? It gives you as many trains as you already know there are for 5 cars. Now, the 2 methods give you all possible 7-car trains because method A gives you all of those that end with CC, whereas method B gives you all those that end with LC. Also, there are no overlaps, right? You're building entirely different kinds of trains by the 2 methods. On the left, those that end with CC, on the right, and those that end with LC. So from this, you can see exactly how many 7-car trains you can make. The number that you can make is the number you can make by the first method, together with the number you can make by the second method. Or maybe I should call them again A and B. In method A, you can make T6 trains. In method B, you can make T5 trains. So, in fact, T7, the number of possible 7-car trains, must be T5 plus T6. Now, that's a rather sophisticated argument, but if you've understood it, it's really the general argument. That is to say, it doesn't just prove things when you have 7 trains. If you have any specified number of cars, this will give you the same formula. Suppose you want to build an N-car train. How can you do that? Well, method A is to start with an N-1 car train. Start with a train that has 1 fewer than the number you want and put C on the end. And that will give you all the N-car trains ending in CC. Method B says start with a train with 2 fewer cars than what you want, and now it's okay to put LC at the end. That will give you all the N-car trains that end in LC. Together, the 2 methods give you all possible trains with N cars, and there will be no duplications. So the conclusion is that the number of N-car trains must be the number that you can build by using both methods, and that is Tn minus 2 plus Tn minus 1.